Okay, good. I'm online. Yeah, Amy, thanks for the invitation. I hope you recovered and can bear with me for the next 90 minutes. Since this is a school, and since I'm a physicist, I won't entirely talk about chemistry and chemical dynamics, but I thought it's also good to talk about more technical aspects, maybe some basic concepts in spectroscopy, because I'm a spectroscopist. And of course, there's the usual response opportunity. And if you feel like there's something urgent, then you can also interrupt if you're if you think this is maybe good to know before I keep going on. Okay, I thought I'll just briefly mention a few things on timing, because free electron lasers are all about timing, I would say. Don't take this curve for, too detailed. Oh no, where's my opportunity here? Okay, here. So obviously, there's some artists here having been doing something. But say early in the 19th century, you had a camera shutter that actually made it possible to take movies, right? You probably know the famous horse, where people were thinking about whether the horse is completely in the air or not when it galloped, and a camera with a fast shutter was able to provide this. So camera shutters got faster and faster, and then there was a period where no technology improved. Until the late 50s and early 60s, lasers came about. And then, of course, you had this really fast drop. And if you zoom in to the last part from 1960 onward, you see that we have covered many orders of magnitude until you actually reached a domain where you could actually not just follow nuclei, natural timescale for nuclei, and therefore for chemistry or phase transitions or matter to change would typically be the timescale of nuclei moving, but of course you also have electrons that are much, much faster. So that would be somewhere in 72, I think, Schenck and Ippen actually invented the femtosecond laser, and then onward you actually got to attoseconds. So you also see that there's the most prominent conference this year actually in Hamburg, used to be called picosecond phenomena. You see it's every 4 years it's in the US, and every 2 years every 4 years either in Europe or in Asia. And you saw that once the femtosecond laser had gotten into labs to a point where you actually had lots of applications that actually beat the picosecond limit, they called it ultra-fast. So this is the ultra-fast line. When I talk about ultra-fast, I typically mean a picosecond or faster, and you see that now we actually have gotten down to attoseconds for electron dynamics, very fast ones. Oh, sorry, that's a stupid animation. Good. Time scales also mean energy scales. Energy scales mean time scales. So if you have excitation in matter, they may be on the milli-eV scale, very small, say vibrations, collective excitations, magnons or the like. Then of course you have valence excitations in the EV range, and then you get to core level excitations in the KV range, and then nuclear excitations in the nucleus. So accordingly, there's of course a natural time scale to each of these excitations, which will typically be for photons, the period of the electric field that does the excitation if you're using photons. And you also have an inherent response of your material that will also be on a similar magnitude. So this you can see here from review of product physics. It's geared towards attosecond science, but I think a lot of stuff is actually happening in between 10 femtoseconds and onward, right? The fastest nuclear motion, any idea? Hydrogen atom, probably. So the shortest period that you have in nuclear motions is the 10 femtosecond of a hydrogen stretching vibration of OH, NH, XH, or the like, right? So typically on the time scale of tens of femtoseconds, hydrogen systems can react, and then larger atoms will react a bit slower. To illustrate some of this, I thought, let's have a look at, say, absorption first. Let's look at dipole active transitions. For simplicity, take a CO2 molecule, and if you move, but this atom has essentially two slightly more electronegative atoms on either side. So you have a dipole pointing inward towards the slightly positive carbon atom. They cancel each other, so you don't have a net dipole necessarily. But when you move the carbon atom closer to one oxygen or the other, you actually have an induced dipole. And if that atom actually has, in a classical notion, moves back and forth, you have an oscillating dipole. So if you have this dipole, by having moved this atom a little bit, right, it will swing back, usually. You'll have a response in that respect, and you will face a dipole in the other direction, and then back and forth and back and forth and so forth, right? So if you try to decide how you could measure this, you could come up with a two-point correlation function in time, which simply means you try to measure how much the dipole is alike to the initial time zero where you started this whole game of say, exciting vibration in this system, right? And if it doesn't stop, it doesn't decay in any way, then you would have, of course, at time zero, you have the maximum likelihood, and then it would actually be fully anti-parallel and fully parallel, fully anti-parallel, and so forth. So in essence, you get a sine wave. And if your oscillation is damped, you see here, this will be damped. This actually, I went through the calculation. This is actually an exponential decay, although it looks linear, but you see that you actually get a damped sine wave. So why am I telling you this? The autocorrelation, or the two-point correlation function of the transition dipole moment that Claudia Draxler talked about, cannot just be classically defined, but also quantum mechanically, of course. And typically, this function here is a sinusoidal wave that is, say, typically damped exponentially. And an oscillating dipole is a continuously accelerated charge, right? It goes back and forth and back and forth. So oscillating dipoles radiate electromagnetic waves. So you could expect this dipole motion to cease, and while it does so, it emits an electromagnetic field. So this brings me to a time domain picture of spectroscopy, which is a very important one. That means there's an incident field. My poor drawing skills here just show this sine wave. It's not pulse, but of course you have a superposition, with a certain Gaussian envelope, and you would have a wave packet or a photon or a flash, which traverses a sample. In this sample, you now create an oscillating dipole, if your sample is actually proven to do so. And this dipole density that you're creating, a density of dipoles, macroscopically is a polarization. Right? A polarization is nothing but a dipole density, which you can also define quantum mechanically, of course. And since this polarization will then decay, it will emit a field, and this polarization is, for one thing, phase shifted by half a cycle compared to the incident field. And the field that is emitted in the course of this damped dipole oscillation will also be phase shifted by half a cycle. So the emitted field, it will be so when you're straight on resonance, right? You're perfectly resonant, and you have a lag in the phase of your polarization that is oscillating, right? Which is this dipole here, or dipole density in your sample. It's oscillating, phase shifted by half a cycle, and then the field that is emitted is again phase shifted by half a cycle. So you get to, quarter cycle. 2 quarter cycles give you a half a cycle, so you're right out of phase, and that is a destructive interference. And that you can measure, of course. You can measure the transmission, and you can depict this just as the intensity that is transmitted divided by the intensity that was before, in front of the sample. And then if you just spell it out, then you get a quantity that you can take the log of, and 1 plus x, if you take a log of 1 plus x, it will typically be, to first order, a function of x. So in essence, what you measure behind the sample is essentially an absorption line shape A. It is perpendicular, it's proportional to the electric field and proportional to the polarization, essentially. Right? So you can also spell this out mathematically a little bit. Here's your dipole correlation function, your two-point correlation function. If that one decays exponentially, right, we know what this means in this respect, right? We're just looking how the dipole decays in time. Then our absorption is the Fourier transform of this decay. So all a spectrometer does is a Fourier transform of the emitted electric field, this one here. Right? Any spectrometer is a Fourier transform device. And then when you actually Fourier transform this function, you'll get the well-known Lorentzian line shape. Right? You have the center frequency, this is your resonance, omega 0. You have omega, or gamma, sorry, capital gamma, which is linked to the decay time. And in the simplest case, you could argue that your decay time is the uncertainty in time when your photon gets emitted if you go from this classical electric field picture to a, say, quantized field. And gamma is the energy uncertainty at what frequency this photon is emitted. Right? And then you have something like Heisenberg uncertainty. And your decay time is always essentially 1 over gamma. I didn't point this out to you, but oh, here we go. Did anybody saw it? What's the convenient unit for H? No one? It's pretty simple, actually. Right. If you have a 2 eV photon, it means you have a 2 femtosecond period on your photon. If you look at the uncertainty principle, H is about 4 eV femtoseconds. Pi is not much smaller than 4. So essentially this is on the order of 1. And then you have 1 over your spectral width of your absorption line shape that you're looking at in EV, and that gives you the dephasing time, right? The inverse thereof. So this decay time is called the coherence time, or the dephasing time. It's an important quantity, and you can read it right off your spectrum under some circumstances. Good. This polarization, as Claudia Draxler already showed us, is not necessarily linear in the field that is driving, or that is impinging on the sample. Right? If the field intensity is high enough, you could actually expand this polarization into orders, into different terms, ordered by the electric field interaction. You could have a linear interaction, that would be your spectrometer, a second order term, right, where the polarization depends on the electric field squared, so the actual intensity dependence is actually intensity squared, and then your third order and so forth. Of course, this whole series breaks down if your intensity gets so high that you would have to keep going with higher and higher terms, and at some point it will not converge at all if the intensity exceeds a certain threshold. And then this so-called perturbative approach of expanding the polarization in orders of the electric field fails. There are actually certain approaches to also have expansions that are not sorted by the fields, but that are correct to all orders in the field. This is more the high energy approach that also people use in Raman spectroscopy for strong dipole interactions, especially in solid state physics. But for molecules, this is usually a way to go for, say, laser spectroscopy, optical spectroscopy, R spectroscopy. But you can, of course, apply this to any like matter interaction if the field is not too strong and you have a perturbative picture. Okay. One thing that I would like to say is that, of course, the spectral resolution, the gamma, that you assign to a spectrum of interest, a material system that you'd like to study, and maybe you have a resonance that you would like to excite to see what it does, right? That is your little hammer that bangs on something, and then you see how all the other degrees of freedom shake and relax, and that hopefully gives you some clue of how things are coupled. And that may also tell you why certain reaction pathways or quantum pathways are the ones that are preferred and others are not, although you think they would be a good idea. Of course, the timescale that you estimate of how far the system can actually respond and go into a new state when you have such a resonance that you want to excite to drive your system out of equilibrium depends very much on whether you have high enough resolution to actually measure the true line width of that excitation. Right. So here, for example, is a little cartoon that I took from Alexander Fröhlich's talk on Heisenberg Briggs, where you see that you may have some artificial density of states here. maybe an elastic peak at 0 energy that would just be Rayleigh scattering, for example. And then you have a phonon 1, a phonon 2, a magnon, a bimagnon, and so forth. And depending on what your resolution is, you will come up with different gammas, perhaps. And that means you overestimate how quick the material system can respond. But in general, if you somehow manage to get the gamma right, it gives you automatically a timescale on how fast the system can respond. Which also means if it's very narrow, it will not respond very rapidly. And you don't have to have huge time resolution for the sake of energy resolution because your system may not follow anyway. Good. So that actually links time and energy scales naturally in any system. We'll get back to a few of these points later. So I thought I'll give you a first opportunity for responding. And this is, I haven't explained everything, but I thought I'll get it. Maybe you give me an impression of what you know and what you don't know. So I thought I'd give you some things that, as I said, I didn't necessarily explain, but it's good to see where the audience is and where I am, maybe, or where I think you are. So, first thing, coherence time and lifetime are essentially the same thing. Lifetimes are always longer than coherence times. Coherence time and lifetime have nothing to do with each other. Completely separate. And light-matter interactions should be treated with quantized fields, always. What do you think? Blue's the color of hope, green of optimism. I would do this. Maybe a bit more green. Yellow. Yes and no, I would say. Red, no, no, no. I'm not a theoretician that works with quantized fields, and these time domain pictures with classical fields mean I'm using many photons in most processes that you can work in a perturbative way work. So coherence time and lifetime are essentially the same thing. If you do X-ray spectroscopy, that's probably true for many transitions or spectra that you look at. Except for a factor of 2, the coherence time defines the lifetime. But then you think of fluorescence molecules, for example. Right? They live for nanoseconds. Have you ever seen an absorption spectrum of, say, a fluorescent dye? Who has seen an absorption spectrum of a fluorescent dye? Show me a yellow if you have. Nanoseconds means must be pretty narrow, right, in line shape? But it's not, right? It's pretty broad. It's tens of nanometers or more. So indeed, coherence time and the lifetime is always longer than the coherence time, certainly not shorter. It can be very long. So coherence time is the time of a superposition state of the system. When you're initially excited, you're creating a coherent state with a photon exciting it. You're creating a coherent state where it's in the ground state and the excited state. It oscillates between the two populations, and eventually you will decide to actually go into the excited state or not. And in core-level spectroscopy, when it has this, basically the damping is so strong that the coherence time, the lifetime, except for the factor of 2 in the math, are identical. But of course, for molecules, for fluorescent dyes, certainly yellow, green is the right thing. And in that respect, could maybe say they have nothing to do with each other, but of course they are clearly interconnected. So I would say first 2. Good. So that was a little introduction to maybe optics in the time domain. I may use these coherence times several times for more elaborate spectroscopies than just absorption. Of course, the goal here is in this lecture to elucidate mechanisms of chemical transformation, right? By understanding the interplay of maybe different degrees of freedom. You have atomic arrangement, it means bond distances, atomic structure. You have the Valix electronic structure that goes along with spin. Maybe there are correlation effects that can also lead to molecular magnetism. So there are many processes that you can trigger when you excite the system with light. Of course, when you go to condensed phase, you have ultra-fast phase transitions, surface dynamics, ultra-fast biological processes. These are in some sense always chemical transformation, small molecules, for example, larger molecules, ultra-fast chemical reactions that take place at about 10 to minus 13 seconds. And I would say from here on, the synchrotron for most things, or for many things, not for many things, the high brightness you may need the free electron lasers. This is the realm of a free electron laser, X-ray free electron laser. The very short part, you have the charge transfer, dynamics, the electronic correlated electron systems that respond. Something that is going sub femtosecond. Of course, you have slower, but still interesting and important processes like vibrational relaxation, energy redistribution, rotational dynamics, things that also are important to understand reaction mechanisms. And just because they may be not ultra fast, borderline ultra fast. One thing doesn't mean that they're not important. It also means that you may actually have better probes at hand than X-rays. So, some subtle changes you may not see with X-rays. So you may want to have vibrational probes or maybe optical probes. Nonetheless, usually you have the mix is the important part. Good. When you go to structural dynamics, especially solution, where I often work at, a ton of methods have been developed over the decades that have all been essentially implemented in a time result. We call XSAF. I'll get to that. If you're not familiar with it, which is the local atomic structure around atom species. Then you have the classical absorption transitions of elements. You have magnetic probes. Then you have higher order spectroscopic methods like resonant X-ray emission, spectroscopy, or just emission spectroscopy if you like. And the acronyms we'll talk about a little bit, which gives you, of course, depending on your energy, low energy, density of states, low excitation, vibrations that are maybe tens of millieV, single digit millieV, which would be molecules of course, and vibrational modes typically are more solid state phenomenon. Unless you look molecular magnets perhaps. So you know probably that X-ray spectroscopy is element specific. It also depends on spin, but symmetry, and that's certainly true for most spectroscopy. You have an initial state, and a final state, couple them by a dipole interaction. Symmetry of either state will play a role. And of course, you can look at molecular systems, their reactions, interface flex and disordered materials are also interesting. Molecules, some things that we will look at. Good. So in the simplest case, you absorption in these two fashions. For the first, you will hear about included fraction, and other methods. So I will essentially talk about absorption and emission in some form. Of course, there's much more. There's the whole business of photo-emission, spectroscopy, for example, which is a big field, which has huge advantages to some extent. But I'll stay with the photons for now. And this is the simple picture. These pictures when you draw these pictures, you have made already a lot of estimations in your head, right? For one thing, an atom is a strongly correlated system. You put an electron here. You're already thinking in a single particle picture. And the fact that you draw a hole here, an electron here, moving all of these levels around, means you have made severe approximations in your head. Obviously, as a theoretician, you wouldn't do that. All of these energy levels may reshuffle in the states, and you actually may not even have a single electronic configuration that is the dominant, would have many reaction pathways where you also excite valence electrons along with the core electron. But let's stick to the single particle picture for now, conceptual reasons, and look at the emission process. So if you have enough energy to kick out this electron, you have ionized molecule, for example, and that leaves a hole here. And because the electrons are strongly correlated in an atom, this core hole likes to be filled by another electron that is maybe at pure binding energy. They have said that if you go to this picture here, okay, this axis is the binding energy. The strongest bound electrons, potential, and these are the lesser bound. And then you have this transition, which gives you a photon. So these photons probe the occupied orbitals or density of state. If you have an absorption event into localized orbitals, you see the unoccupied. Of course, that is also true if you go into the continuum. That may not be that interesting unless you measure the kinetic energy you kick out. That would actually be the difference between the photon energy you put in and the binding energy, the kinetic energy. In that way, you would also measure the occupied density of states. So emission and photon electron spectroscopy, in some sense, measure the same density of states. Of course, there's selection. Those are these things that also matter. So for nomenclature, X-ray absorption spectroscopy does have these edges. Like you have these again in these single particle pictures. These levels. You have electrons tightly bound tightly, and so one is P and so forth. And the nomenclature denote these absorption jumps that once you have enough photon energy to actually promote initial electron continuum by letters, namely K, L, and M, and so forth. So an nitrogen atom obviously only has 2p, and 1s electrons in the ground state, and then you have more than one unoccupied 2p or 2p or into the continuum. Only have k edges there. For transition metal, third row you would already have 3d electrons. That would also allow you to have L edges. And then M edges and so forth, depending on how heavy the whole thing is. But I will only talk about K edges and L edges, and mainly K edges actually. Here's actually a depiction of some differences that you can already appreciate. These are not so much differences between L and K edges, but more in shape between say soft X-ray transitions and hard X-ray transitions. You say that the edge jump that is depicted here is essentially the jump this level here. This one here. Hopefully you can see the red. Between this level here and this edge jump. The edge jump. Of course here you also have the same edge jump, except it is much smaller. And you see that means that the resonance cross section is actually larger when you use softer X-rays, for example 3D, then going from 1 to 4p. But the resonance transitions are also much stronger. So if you're interested in the unoccupied states, the unoccupied orbitals that you want to with a localized 4 electron, you actually may have larger signals, and interpret your system. Also the system changes when you go to L edges, K edges of lighter atoms. Then when you work in hard X-ray, the cross sections are generally smaller, and also pronounced resonance transitions are smaller. Good. The next thing is that of course X-ray means you're looking at the table, your element specific. Every element has a unique resonances and X-ray edges there where you can work. Certainly very important ones are transition metals for X-ray spectroscopy, but also the lighter elements of interest. That of course depends on your specific field. But clearly, any edge, if your beamline is properly calibrated, exactly what element you have. That's quantitative. So you can actually identify exactly what kind of atoms you have in your matter on your solution. It comes in handy. The first part I would talk about is absorption fine structure. Also maybe a little bit in the time domain. If you do, I have to see how it works. You do promote an electron, say from the 1s orbital into the continuum. You actually have created a free electron. Right. And this free electron doesn't have too much energy. Certainly non-relativistic. It becomes relativistic. 10% of the rest mass of an electron. Or free electron that would probably be on the order of 50 keV. So since it's 511 keV rest mass, it means the excess energy that the photon can provide, or the electron, or the extra energy above weakly bound orbital, then the kinetic energy in a simple way, and that well-known formula from Q squared to 2m of 1/2 mv squared kinetic energy. So your photoelectron essentially is a particle. According to Dimorghi, it has a wavelength. So you can assign a certain wavelength. You can also consider the ionization event that generates this three particles as a wave that is emitted at a certain time. And the neighboring atoms will scatter this electrons scatter on the nuclei, but also charge density. And that means you have a backscattered wave. So in that respect, think about optics. You have two wave packets, two electron wave packets that interfere. And one picture to look at it is that if you have take a light pulse now, maybe it's a bit simpler to envision. You have a light pulse, you Fourier transform, you get its spectrum. That's what the spectrometer. If you have two identical pulses for simplicity, you have the same spectrum. You also get the same envelope, but you get interference pattern, and the interference fringe spacing in the frequency domain, energy domain is just inverse proportional to the time. So EXAFs in some sense. You're looking at electrons changing wavelengths, but also the time domain. You suddenly have ionization event. Your electron wave travels outward from the nearest neighbors at a certain distance, which will point in time interfere with itself, and then you get this spectral interference. There would be one way of looking at it. And because the interference pattern will depend on distances, they all add up here. Complicated wave distances. You will see this. Of course, this oscillation is quite small, and if you change the system, the changes will be even. But in principle, you have basically a Fourier transform of the nearest pair correlation function. And of course, the scattering amplitude in circle wave typically. We'll get it later. Dies off very rapidly, typically with k square, or maybe even faster. What you typically do is you assume that you have a step function of some completely empirical. You get rid of these resonant transitions by just multiplying zero essentially. Only left these oscillations. You say this is the Fourier transform of my correlation function. And now, since the amplitude vanishes very rapidly, I can actually multiply this by k squared power, which just means oscillations. And if you think back, I should have put this in here. All you do is basically deconvolving in the momentum domain, like as if you were to actually try to multiply time-dependent signal t squared, so the time squared power, actually try to get rid of this decay. What does the decay do? It just makes the line shape broader. So all you do in EXAFs this k square or k squared power, the third power. Multiplication. Yeah. This part here is actually try to get rid of the damping oscillation, the momentum domain, and in real space actually deconvolve the pair correlation function to have sharper peaks. In this example, you have chromium hexacarbonyl. You see the nearest neighbor for carbon, chromium and oxygen. And the nice thing is, of course, that you are short-sighted. You are extremely precise in determining even for an isotopic example, the nearest neighbor. And if you're in a crystal, you could still do the same thing in isotropic EXAFs oscillation. If you change that, then you also change isotopic changes. Good. So that's EXAFs. And of course, you can also do time resolved. So people haven't really done this so much. So I think this is one of the opportunities for LCLS2. Can see here. This is an example. Which I would like a bit longer. Technical reasons. There's many interesting aspects of this work. It's about theory of structural dynamics, and you see that there's the onset of X oscillations here. Of course, also see the resonant excitation. So this is the iron KH. Here's the energy incoming X-ray photons. That's Sakla in Japan. The 1s binding energy is on the order of 7,000 electron volt. When you excite this system, you actually launch with a UV pulse. Launch complicated chemical quantum pathways, right? And then the system undergoes for one thing metal charge transfer excitation. When you excite the system, you then have a structural change, and they also see dissociation, and you end up with a different molecule. So here you see the static spectrum, and then you see transient spectra that they have reconstructed from this difference. In pump probe you can measure differences very well. Reconstructing the spectrum is not so easy because you need to know the excitation yield. They've done this, and what they see is a characteristic upon LMCT excitation. So this is an electron that formally gets promoted from one of the three ligands, the metal center, which is the iron. So you go from iron 3 to iron 2. And in the simplest picture, you would say, now I have more valence charge density on my iron here in the center. I've changed the oxidation state, and I have more valence charge density that has a probability between the 1s electron, more strongly bonded, and because we have screening, and that binding energy is actually reduced. This would be a very simple particle picture. Here we will be more complicated, but gives you a qualitative way of understanding these spectra, and maybe So you have what people call level shift. The 1s electron strongly screened from the core. That means the binding energy is lesser, and then the valence unoccupied the virtual orbital do not react as much to this additional valence charge density, and that's why you have an absorption line chip that is red. You need less energy to grow more than some unoccupied 4p orb. That's the idea. Okay. Of course, you have a spectral axis, and you have time delay axis. So you can also magnetic analysis to figure out which part generated when the structural change occurs, smaller one and the larger one. You don't want to necessarily go into the details of the science of the system, although they may be interesting. But I thought since this is a school, we should also look at the technical aspects. So for one thing, this is a schematic of the setup. They have their X-ray beam coming through. They have a so-called I0 monitor. So they measure how much intensity on every shot arrives at the sample. And then the sample gets excited. There will be also emission inadvertently. And if you collect emission without resolving the emission, you actually do get a measure that is very close to the absorption spectrum. At the same time, they also have which is not shown, where you can actually measure the transmission X-ray intensity. And then they have another beam, this harmonic of a sat laser, 6 EV, fairly intense UV light, fairly high voltage energy, which then excites the sample before the X-ray comes along and measures it. So you see they have pretty good correlation between the fluorescence intensity measure on every single shot, I0 with the I0 monitor. So they can normalize every shot with the I0 intensity measure, and then get a spectrum that is the one in red. I haven't done this. Okay. Let me get to it. They also recorded the absorption, transmission spectrum, or the absorption spectrum that you get from the transmission. You move through your X-ray energy. And you clearly see that the emission spectrum, total fluorescence yield spectrum, superior in quality. Probably at least I would say a factor of 2 to 3 in the data. You can't really tell. What I've put on the next slide is that the concentration for the black sample is 5 times higher. So we have at least an order of magnitude better signal to noise. which tells you if you have a SASI FEL, don't do transmission. Transition is not idea. A bunch of transmission is what you see is what you get. There are some tricks when you do fluorescence yield, I'll get to some, especially in the soft X-ray range. Okay, so we've established that fluorescence yield is much better. Do this. Why does it win? Transmission. You think about transmission. Here's an example on the ALS, where we measured manganese complex. And you see this is just transmitted in some arbitrary volt or something. Some current in our photodetector that then voltage as a function of X-ray energy. And the black line is what you measure. This is some sort of transmission spectrum. If you put a straight line on top, you would get your absorption spectrum. You see how small that is? If you zoom into this part here, you see that only a few percent of the transmission are diminished by the absorption of the manganese ions in this system. Right. Now you excite this system, which only has a few percent change when you scan through the edge. And these few percent, 1% or so, can alter by maybe 1 or 2%, maybe 10. Right. You're really kicking it maybe more. We get to that part two. So you're only looking at typically a few percent of a few percent, 10 to the minus 4, 2 times 10 to the minus 3 or so. In fluorescence, you measure directly. You have a measure of absorption directly. If you excite 20 molecules, and each molecule changes its absorption spectrum at some energetic position by 10%, 50%, you actually have a change of 10% of your fluorescence spectrum versus 1 or 2 orders less magnitude less in transmission. It's just a virtue of transmission not being a background-free technique. We measure a tiny change in photon flux on a huge photon flux. Whereas fluorescence just measures essentially for the elastic background maybe the photons that got absorbed and now being re-emitted. Okay. So you say, have small signals, I can do fluorescence yield 10 times to noise probably. This measurement here, you see 100 millimolar. These are fairly high concentrations. Ask somebody to make a protein for you, because you want to measure a metalloprotein, and the whole thing, the catalytic function of that thing. You'd be lucky if you had 1 millimolar. That also explains why you actually got transmission spectrum at all. Now you say, okay, let's crank up the power so at least we get to noise. You get this 50 microjoules, 40 microjoules. And then you see how the transient signal actually rises. Something like this typically won't find in FEL publications. You also won't find them in laser lab applications, data from laser labs. But I think this is actually very insightful and important in some sense. And I thought let's go through some numbers. So fortunately, this paper gives you pretty much everything you need. And it gives you something that you should know before you even write a proposal. Remember, right? And remember, right? Of 5 days at an FEL, $1.5 million to 2 million, 120 million operating budget, 40 weeks of operation. Typically you have less. That means 30 per week, million per week. 12 hour shift. Old days times 60, with 1.5 million. So you better understand what you're doing. Although I always know what I was doing. Sample thickness, 50 microns. Concentration, fluorescence yield, 100 millimolar. Molar absorptivity, 5,000 per mole per centimeter, for example. Technical. These are experimental parameters. It's chemical. You measure the spectrometer, absorption length, 9 micrometer. Absorption cross section, 10 to the minus 17 square centimeters. You can just calculate this from your epsilon. What was L again? This is just the conversion from cubic centimeters to liter. Because cubic centimeters match this number, whereas liters are deciliters, which match the molar. So this conversion factor, the epsilon, Avogadro's number, all you tens, from the epsilon you can directly measure and calculate the absorption cross section. Pulse energy, 42 microjoules. Pulse duration 100 femtoseconds. To be focused, they estimated 150 microns. Then you get to a fluence of 130 milliliters per centimeter, or over 10 to the minus 17 photons per square centimeter, which means you have about 3.5 photons per molecular cross section. And your peak power density is 1 terawatt per square centimeter. Okay, okay. Look at the numbers. They chose that. This is the paper. Okay. I'm just giving you the numbers from the paper. It's all in there. So now, check the numbers. If you see any flags, remember them, and think about this. Four statements again. All optical parameters are similar to laser lab experiments. Say conventional, not doing harmonics. You would do this experiment, same excitation in a laser lab where you have a UV this broadband continuum, and you want it to probe. The peak power density is a bit high, but not alarming. That absorption length looks quite short, and I should start thinking about solvated electrons. You have to raise that paper. Everybody looks forward. You don't see what the others are doing. Nobody gets embarrassed. We don't have clickers, but just straight forward like a horse. With these things on the side. And make up your mind. What about the back row? You want to see my choices? Let's go back. 50 micrometers. For transmission. When I do absorption length for lumbar beer, 9 microns. It's 4.5 times the absorption, the thickness of the sample. So my transmission is absorption length e to the minus 4.5. E to the minus 3 is 4%, right? And then 4%. So you have maybe 1% transmission. So you're losing a lot of photons. For transmission, certainly too thick. If you are under certain circumstances, let's say. What about total fluorescence yield? Does that care? Big question is what is the absorption length of the X-rays? If we're working with hard X-rays, certainly hundreds of microns. So your X-rays either penetrate the whole thing easily, or the fluorescence that gets excited in you also coming from the entire jet volume. So you're looking at a tiny fraction if you are in the I would say in a sane regime. Leads me to the next question. A bit high, but not alarming. What the heck? 1.3 terawatt. I mean, non-thermal melting of silicon is a bit denser. It's about 100 milliliters per square centimeter. We are already well beyond that. So I'm sure that jet is close to explosion. That's abnormally high. It would never work at these in a laser. You could easily do with 1% of this. And you would still get a good signal. So that's characteristic for FEL solution phase chemistry. And of course, you have only a few days of beam time. You want to have that signal so badly, and the publication. You crank up the power. I've done that. But you at least have to be aware that you're doing it. Why would that be a problem? Hey, let's check, for example, two-fold absorption of solvents. All this nice paper. If you think, these who would read these papers, but then you find them. Wow, great paper. So you see, two-photon absorption cross section of certain solvents, methanol. You see that basically it scales more or less linear with atomic mass. Something you would expect. you can do the math. You can do the math. So you have the cross section, sigma 2, two proton cross section, and then you have your fluence squared divided by your duration, because two photon absorption means absorb two photons at the same time. So they have to come in close temporal proximity. Right? So time duration is critical. Peak power. So you put this in. 0.3%. Who cares? You have water as a solvent. There's not really anything that is more dense than water. You have 55 molar water concentration. Usually people don't think about solvent concentration, but they're typically in the range of 20 molar for alcohol, organic solvents, and water because it's so small. And then it's 55 molar. And then that 3% suddenly turns out to be 165 electrons. If you assume that all two photon events lead to photoionization and give you expel a photoelectron hangs around in the solvent. So that doesn't look so pretty, I would say. And then the next thing is, okay, you've cranked up your power. How much can you actually expect to excite in the first place? Obviously, you have the problem that you really want to excite a big quantity, and you have the dilemma. If you excite it in a very short amount of time, you actually have other events kicking in, like optical, nonlinear spectroscopy, or nonlinear optics kick in. And you certainly want to avoid this, but maybe you cannot because you need that time signal. The other thing is a transition dipole is a vector quantity. So in an isotropic ensemble, like you have in solution, everything keeps tumbling and tumbling. You have a vector quantity about one third of the molecules per dipole, transition dipole moment, roughly get the average over this p squared. Distribution of dipoles aligned to your electric field, and your electric field is polarized. Then you get a third. This one here probably has three transition dipoles. You have ligands. They're all identical. So you have some symmetry, and will probably allow you to have a metal charge transfer from each of these ones. So with three dipole moments that are not perpendicular, but parallel, fairly differently oriented, can probably get something that if you had a longer pulse duration, for example, wouldn't we have these higher optics events? Probably get to 80-90%. So if you use picosecond lasers, you shrink the peak power density. If you use the same parameters, but you go from 100 femtoseconds to 1 picosecond, 130 gigawatts per square centimeter. That's already a whole different ballpark. Because this would mean 1% of the 0.3% absorption, and then you say millimolar as a rough estimate. And then actually people have done measurements where you actually see 80% conversion picosecond. But that's an inherent dilemma for femtosecond time resolution. You cannot just arbitrary amount onto your sample. Actually get high changes. And that's true for not any system, solution-based, but of course here you also have tropic ensembles. So you can't orient your dipoles in the direction that you want to actually have some efficiency there. So you lose out doubly. So that's probably something to consider if you go to an FEL. And all of these experimental parameters can be checked before you write a proposal. Design your experiment properly. Not wonder what new chemistry you have found. Papers are out, but they do have probably some flaws in them. Especially not just some of this you can check, of course. What we haven't discussed is the solvent transmission. So Center for X-ray Optics, Berkeley Lab has a nice database website. You check solid would mean condensed phase, liquids, and you check, for example, the solvent transmission. Here, for example, 100 micron convenient thick experiment. You see above 5 kV, ethanol, more or less so different. Not so different. Soft X-rays, typically below the blue line. Nothing. So you can zoom in. Oops. Oh no, I lost my slide. Yeah. This is not cool. This is not cool. This is not cool. This is not cool. Sugar. Okay, let's improvise. Let's improvise. I don't have that. That's not cool. That's not cool. They vanished. They vanished. After deleted. Anyway, what we're gonna do is we improvise. And we have right. Then let's do a little practical. Let's do a little practical here. No. Update. There you go. Okay, all good. Should have this here. Yeah. Well, maybe it will let me. In. So, I want to show you what it looks like in this regime when you have 1 micron instead of 100 micron. Let's continue until I get some signal here. Let's check. Oh, there we go. Look at this. Okay, easy. Solid. This mask here. Just depends on in there. Trusted. 1 micron. Let's go from 100. 1,000 steps. There you go. Right. So you need on the order of a micron thickness if you want to do soft X-ray solution phase spectroscopy. First place, time resolution. That's the same. And you see here nice illustration of the water window. Actually, second. The second water window. Third, if you like. Where's the most prominent one? Where's the most prominent water window? Look at this color here. 490 nanometers. Caribbean. That's where water has least absorption. That's why the beaches with the white silicon dioxide on the bottom have this color. Right? The water goes in. Of course, it gets absorbed and scattered. But the absorption minimum of water is at 490 nanometers. That's why. It's not the sky that is blue, but what is. So the second one is obviously this window here, water window, where you have nitrogen KHs, you have carbon KHs, and of course you have this big drop when you get to oxygen. But with 1 micron thickness, you can do sulfur will be tough, 160 eV, but carbon and hydrogen, titanium 520, also nice, very high transmission. Other one. C660 is ethanol, 0.789. Same thing. And you see a bit of oxygen here. In front of the carbon KH, now you can do sulfur, probably 40-30%. Not like your transparent solvent in an optical lab, clearly. But in IR you have similar problems. Here you see the big drop of carbon KH, and then if you get to manganese, LH, or iron, nickel or so forth, actually it opens up again. So if you want to do work with soft X-rays, it's still an important quantity, not just because you may want to get through your solutions, as these people have done. Go back and get this. Right. Ultra-thin liquid jet technology, flowing tens of meters per second, so you can exchange it within microseconds or less than microseconds. This is Eric Nibbering's group, who bought the first microliquids jet, two nozzles of thin nuclear microjets colliding, and what you get is essentially an oscillator. Momentum spreads to one direction. The liquid wants to be round, so it bounces back, other direction, back. And then you see nicely here the oscillator. One leaf here, the other one is. But this is a sine function. The other one is a cosine function. Oscillator. Because you have two jets with momenta in directions that span. And that way you get 1 micron or less thickness. And there's different approaches. In essence, they all have in the end two partial beams that collide. Here you have a nozzle with a ridge in the middle, so that means you have the nickel jet and they collide as well. Expand the leaf. Here you also have virtual gas nozzle, which that's slightly different because here in the middle, and then you have the helium from both sides that actually squeezes it down. The nozzle is asymmetric, and then it will also relax oscillation by oscillation. This way you can actually very thin jets. Alternative would be in transmission. I can do this in fluorescence here. I haven't shown this in a while, but it's still very instructive. This is the oxygen kH of water in water and acetonitrile. Increase the water content, and would expect that of water form, and then the water get bigger and grow. And then this is the evolution that this group in Berlin measured. So increasing water content means you get from pink to cyan. And they deduce that you can actually assign these transitions that are fairly localized in gas phase and well-defined. This here is a sort of resonance that you only have in liquid or ice. It's most pronounced in ice. So this one goes down, and this one you increase the water content. So they thought, okay, the lowest water concentration measured in nitrile is mainly symmetrically bonded. The structure of these molecules differs from the gas phase or liquid water, ice-like. And they also say induced increase of the positive intensity absorption fluorescence can be related to an increase in orbital hybridization of the H bonding, stretching the hydrogen between the water molecules. The orbital hybridization increases when you stretch the bond. That's bullshit, no? Come on, you stretch a bond in the extreme. There's no more interaction. There's no bond. But if you follow through with the spectroscopic interpretation, they're right. But they increase the orbital hybridization upon stretching the hydrogen. The hydrogen bond is defined as two oxygens with hydrogen between one oxygen, and now you stretch the bond. You stretch the distance between two oxygen bonds are mainly dipole interactions. They're fairly short range. Stretch the bond, increase the orbital hybridization of this moiety. That's bullshit, no? Come on, you agree. This is what you get in transmission. You see the arrows point the exact opposite. When you increase the water content, the whole thing becomes isolated water, gas phase like large and larger water domains. So you're approaching the red line, which is water. Why is that? When you work in fluorescence yield, you can have very short absorption lengths in the soft X-ray regime. So for this peak here, you have about 500 nanometers to go in. So you have a very small volume that can actually fluoresce, give you a signal. Here, the absorption length is already 2.5 times larger. So your absorption length is 2.5 larger. And your volume grows substantially, and you get more signal. So this is a classical saturation effect that you see here. But if you're not aware of this and follow through, this is what you get. And if you don't realize that writing hybridization increase when you move to atoms apart, then this is what you publish, right? So no. The real story is short. You have these unoccupied orbitals. You have two unoccupied orbitals. These transitions here for water. You can probe ice in different ways. You can see the bulk has really strong resonance in the back, typical of very localized charge density here. Sigma star resonance. You terminate the dangling or H bonds that are more gas-like. So you also see these resonant transitions disappear. Compare this. Brown is the gas phase spectrum. You look at you look
isolated
at
water,
acetonitrile, very weakly bound,
hydrogen bonds.
You see that the red spectrum is essentially
at a little hump,
which is
a bit like a Fourier transform.
The lower the energy of this hump,
the longer the bond.
And then you see continuous distribution towards ice.
So that all makes sense.
And then you can also excite, for example, vibrational mode, thermalization
of the thing. This was actually done
for electron lasers.
Very painful experiment. I must admit.
The black dots
were taken a few years earlier, an hour or so, on an infrared absorption experiment. 3 microns and probe with 800 wave numbers, 13 microns, and you see that many years later, difference in photon energy of 2000, you get the exact same thing. So some things are just better done with IR and X-rays. But nonetheless, one of the reviewers actually said it had to be done. So maybe this is a good reminder that there is a world of ultra-fast science out there, and not just X-ray. There was a recent PNAS on ultra-fast normalization of water within femtoseconds. They have ignored 20 years of ultra-fast IR water research. So I thought this was a bit ignorant. Anyway, let's get on with it. So this is I don't. Good. Next opportunity. 20 minutes left. Any solvent will work for soft X-ray transmission experiments. Why use X-ray absorption? There are better ways to do it. Why bother about solvent ionization? Diffusion is slow. Or sorry. I use hard X-rays. Hard X-rays. I don't need to care about solution thickness. What I do. Red, green. Patches of indecision or boredom. I would tend to blue, maybe a bit green. Although Amy's here, and the co-author of this last paper. The thin jets. In principle, if you get it thin enough, it will probably work for any soft X-ray experiment. Say if you define soft X-rays carbon edge onward or so. Problem is of course things get very thin. Thin means very little sample. So another good reason to have high rep rate. Good statistics. Like you don't want to work with millimolar on 10 microns or so. You can't, and you can do with much less. Concentration and sample thickness, and then you need megahertz rep rate laser, X-ray laser rather than something else. Why use XAS transmission? There are better ways to do it. Yes, maybe. Right? For the reason you don't have a seeded FEL, it's very stable. If you don't have a good normalization scheme, there may be better ways to do X-ray absorption, spectroscopy at SASI FELs. Now that you also have heard about it, you can also in optic lab you have a phase beam. You don't split the beam in a way that you put a knife edge in the middle, but you actually have a beam split, phase front beam, but then you have two phase shifted by pi roughly. And you can do the same with the zone plate now. So you can generate two beams, put them through your sample, one reaching the other one goes to the sample. The sample fluctuates, the intensity fluctates, and you can normalize this very well, and then probably transmission is the way to go. And you know what you see is what you get. Right? You don't have harmonics that also go through the system. Then transmission is more reliable and gives you absolute absorption cross-sections. Diffusion is slow. Maybe for the first femtoseconds, but you don't have much space to excite them. Like if you're in the if you're in the tens of millimolar range, nanometers, and then nanometers, and then diffusion will kick in maybe on interesting maybe that doesn't really count. I use hard X-rays. I don't need to care about. What about timing? What's the refractive index of your solution? Now you ask me, what do you mean? X-rays or laser? Optical laser. Typically 1.3, 1.4, 1.5 for optical frequencies. The frequencies that where you excite things, UV maybe, IR. For X-rays, it's one, right? Basically like vacuum. So your two pulses pass each other at considerable difference of speed, 30%. Speed of light for the X-rays, 70% for the laser. So you get temporal smearing in 100 micron. You won't get your time that you think you will get, or you hope you would get. So the thinner, the less temporal smearing. You can't avoid that because as long as not using X-rays to pump, you will have index mismatch. Very common when you do for example, but also here. So you should care about the thickness at least on the order of 100 microns or maybe 30 microns. Good. Give you a few examples. Running a bit late. I'm talking too much. Transition metals are nice because they have very well-defined edges. They usually at least in molecules, oftentimes minority species. You have many carbons that see well, nitrogens or other small elements. Transition metals, they're usually the key to the functionality of transition metal complexes. And you have a few of them. So X-ray spectroscopy is nice. Of course, in particular, ruthenium is a nice playground on the chemistry side, and maybe not so useful. But I think for understanding spectroscopy is still a nice system. Photochemistry is fairly simple. The ruthenium ion is an oxidation state 2+. You have six paired electrons. You excite a charge transfer state. That basically means you transfer formally an electron to one of these pyridine moieties, and then you quickly have through spin orbit coupling, say in tens of femtoseconds, go from a singlet state, because this one is dipole interactions preserve spin, go to a triplet state, and back via fluorescence. Fluorescence is also a dipole transition. Stuck here for tens of nanoseconds. Not so exciting, but you can work in single parts and understand different types of spectroscopic absorption. For example, you do an X sub 1 S25P and beyond, and you see these are the changes here at region and here the absorption difference for this molecule when you go from 1 S to 5P and beyond. This is fairly high energy because it's a transition metal complex 22 keV. And you see now that when you take the black spectrum, shifted a bit, subtracted from itself, you get the blue line. When you do a pump probe measurement, you get the red line. Because they're so similar, it basically means the structure is determined by these oscillations. If I can ground state spectrum from itself, just by shifting it, I haven't changed these oscillations in the excited state. The structure is the same more or less in the excited state. I've only shifted the spectrum as a whole, and that's typical of an oxidative shift. The ion is now going from 2+ to 3+, because I have largely on the ligand, and this is just a shift. And you can picture it as a polar shift. You have now less valence charge density. You have less screening of four electron, and then higher binding energy. For the valence electron reacts so much. So transition is blue shift in this case. LMCT, lower oxidation state is red shift. And this is a blue shift. Photoemission would be the opposite. But think that's the same thing. Good. So this is just a shift that you can nicely see. Now we go through. We take a different probe, 2P to 4D, and the 4Ds are the valence electrons. So now you excite this system. You get this differential spectrum. You see here, you have the old transition of the ground state vanishes. Less absorption where your ground state absorb.
This is 2p,
This is 2p
4d, and you have
unoccupied 4d 5d orbitals.
5d orbitals.
In the ground state,
Three
of them are
three
lower.
of them are lower.
So for T2G
So for
orbitals,
T2G
they're fully
orbitals, they're fully
occupied.
And
This transition here
is now
vanished.
or has gotten weaker.
Essentially has vanished.
You have a new transition.
Positive absorption change.
It's the same
Transition
as the ground
transition
state,
as the
but
ground
this is where
state,
you
but
have the
this is where you have the
oxidative shift.
Right?
So binary energy goes a bit
So
up.
this blue transition is basically now shifted to high energy.
So this is just
oxidative shift.
less absorption in your ground state,
reduced absorption,
excited state.
and you have a new transition.
Right? You have one
Right?
electron,
you have one electron orbital now.
so you can promote
So you can promote
p
your
electron
p electron into a 4D symmetry orbital,
which is this one.
So the 4D transition metal,
the one electron picture.
works quite well.
This is the typical signature of
charge transfer state.
So
the message is
X-ray absorption
near structures
can give you
nice information on
electronic configuration.
Not always, but
in here it works
really nicely.
You can also go to
ligand
KH.
hydrogen 1s,
Hydrogen 1s
to 2p.
No other orbitals that are really
relevant
relevant
here.
These are hybridized
with the
ruthenium 4D.
And you look at the different spectrum again.
This
Hydrogen 1s to
hydrogen
2p
1
has
one very pronounced
absorption line shape
around
399.5 eV.
And this obviously
is bleached.
This was taken at the ALS,
not so.
And you see two
And
new
you
absorption bands. So
In a similar
naive way, you would say, okay, here you have
here
an absorption
here
of a
transfer state.
It ought to be a bit more complicated. Time is only
7
picoseconds.
But you do get additional information from the ligand.
So you basically get
structural information
from the KH, electronic configuration of your transition metal ion, and you get additional information that we still have to decipher from where you actually have put the electron. Good. Another thing is that
you can modify
a system.
And look, you have two types of pyridyl nitrogens here.
These ones here,
and these ones here.
and they're all bound.
You would think
Stay away of
if these were fluorines or sulfurs,
I would certainly
be able to see them.
would distinguish them spectrally. But what about
These type of
very similar nitrogen species? When you change from morbidity to
extended ligand,
your electronic configuration will do the same thing.
In the
signal to
measurement here,
blue and red traces
are the same.
Red is morbidity as a reference.
The one with the extended ligand
looks the same. So your LHs are pretty much insensitive to the fact that you put something here chemically.
You do see, however, that
there is a strong solvent dependence.
The nice thing is that
sitting on
one of these peaks here
in
the
change of absorption when you excite the system,
and
the decay of this signal clearly tells you
that
the charge transfer state that you have excited, this charge transfer state you have excited is decaying.
There's
orders of magnitude between the different types of solvents.
And it's not the polarity.
It seems to be the ability to form hydrogen bonds. Although
fairly conjugated
system. I don't know.
Question is where.
So at least you have an equivalent of your electronic configuration.
5 minutes.
Okay.
Speed up a bit.
And you see here now.
This is a difference.
Blue is morbidity.
We know what's going on.
Transfer state. And red is now the extended ligand.
And what you see here is two bleaches,
reduced absorption.
These were the initial two absorption bands.
You nicely see that they're chemically very similar. These are the nitrogens that are coordinated
metal, and these are the
covalently bound to the other carbon atom. And when you place an electron here, they will also shift. So maybe another response opportunity. And I'll steal 5 minutes. Salvation effects are negligible in X-ray spectroscopy. Single particle pictures only work for KHs. Work well for KHs.
Probing multiple edges helps metal ligand interaction. And forget some X-ray spectroscopy. I'll use X-ray Raman scattering. I have to be quick now. Good for you. I would also probably say yellow. The fourth row transition metal LHs also work pretty well without too many multiplex contributions. Third row LHs big problem theories. Especially when you look at nitrogen K edges, for example, say ligand K edges, and you have to take the metal center into account. And in principle, LC-2, Raman scattering. We get to this in a minute or so. Would actually be an option, perhaps, but it's photon-hungry, so maybe soft X-ray spectrum. The other thing that I want to touch upon, X-ray emission. It's the fact that once you have absorbed, there's about 10% chance of emitting photon and 1% X-rays, soft X-rays, and they go typically for pi, but you can collect them. If you have enough photon flux, get a very decent signal, background free. And if you use special crystals, you can also get chunks of spectra covered, so that you can do larger parts in parallel geometry. And then you get emission spectra. Also give you. You can implement in time resolved way. Here's an example of the very early developments of this technique. From a couple of years ago. And here's a more modern one. You probably know Kelly Gaffney's group, where he looked. He excited resonance. So you ionize them. Right? He kicked out a 1 M4 electron, and then a 3p electron, which is called a K beta emission line, fills that 1s4 hole and emits a photon. Now you could argue that this is not where the music is free, because the valence levels are the 3Ds. Now iron is ruthenium. But an atom is a fairly strong electron system. So of course the 3Ps will have exchange the 3Ds, less so with the 3Ds. So they basically sense the electronic configuration. You can also see that reference compounds to look at different electronic configurations, and you see the different spectra in emission that you can get. And when you follow this line, you can also see that for transient triplet states, you have an increase in emission at this energy here, whereas you have a reduction for a quintet state. And this is the data that they published in Science, where they had a high level of confidence, statistically, mathematically, not to say that the system must go spin cascade, and this triplet state had been looked for 20 years, and by now they have better data, but basically convinced the editors that you understand now these polypyridyl iron complexes very well. There's much more interesting stuff too. Another thing, of course, is that you don't go above resonance, on resonance. Spare you the more elaborate theory about it. Just general Raman scattering. Raman scattering, you would say, is a vibrational spectroscopy technique, but in the end, it's very general. You put a photon in, you have some scattering, probability, and then you get a photon out, which has either lost energy or has gained energy. And that quantum of energy that you have lost or gained is somehow some excitation in your material. It could be a vibrational excitation. It could also be a valence electron excitation. It could even be core level excitation. Hard X-ray Raman scattering. You could kick in 30 keV photons and lose 530 eV on water, and then you have a core level excitation of oxygen S to 2p. And you could measure soft spectroscopy with Raman scattering. It was extremely photon hungry for LCLS2, potentially an option. So this is the picture, the total energy depiction here. Put in energy 400 eV for nitrogen K as 300, get out 300, you have lost 7 eV. Right? And in a single particle approximation, you have a resonant absorption 400 eV. This electron falls down, dips into 7 eV. You actually are the final state of this process is a valence excitation. and maybe just briefly done an experiment a while ago, but now we're ready to publish. Write up. Probably been wondering about this. Too bad. Yes, I'm talking too much. Anyway, you can do at LCLS at one. You see that the noise is one photons per shot, so you really want LCLS. The benefit is that you actually get new information on systems that you cannot get with higher resolution, and new ways of actually looking at this. You can see transfer state in materials and composition you cannot get. So the fifth opportunity is probably a stop from Amy. I have 50 backups left. I probably wouldn't get it. Can we do this one and then do this one and then do this part of it as part of it? Last opportunity anyway. XCS is insensitive transitions start from valence states. Having to be above an absorption for XCS is a problem. Femtosecond rigs can provide elements visible spectra. Rigs is a nightmare. I'd rather stick to X-ray absorption. Last chance. Okay. You're punishing me. Green. Would say majority says yellow. I would opt for yellow. It depends on what you say. Okay, XCS is not insensitive because you have electron correlation. So even if you have beta emission, you still sense the valence states. You could also do valence to core, but that's much less likely to happen. So you need more photons. This could be a technical advantage. You don't have to actually have a narrow band monochromator. You can just go above the broad spectrum, take all the photons you can get, and sit in an absorption range where it's essentially flat. This is actually a benefit. And formally it's not dipole transition, but you get from rigs, but you get element specific valence excitations, and that's sort of equivalent visible spectra, but now element specific huge advantage. Rigs may not be a nightmare for us. Okay. So formally you have 1 minute. Maybe you don't want to ask me any questions, or we'll just take an extra 5 minutes. The really cool part is this one. Okay, thank you. I give you this in the meantime. I have exhausted you. I was a very quiet child. Anyway. Are you all solid state AMO theoreticians? Maybe not. Oh, it's lunchtime. And you're hungry. Your blood sugar is low. We closed the session. For lunch. Oh, sorry. Say stop. The nitrogen or the iron? Yes. This is it's a. I mean, with the X-ray over the laser. So it's 4.6 EV excitation in the UV, which triggers multiple reaction triggers ligand loss, triggers intersystem crossing, and you actually for every pixel that you see in this 2D map, this is the photon energy in, this is the loss of the photon energies that you detect when they come out. This is the energy that the system has, that the molecule has absorbed or has given off. And for each of these pixels, you have a time delay. X goes into the wall. I think the reason why this got into nature is that you have a laser pump. You could promote one of these electrons, say to this orbital, and then one of them hops down. Or this one hops into the unoccupied orbit. You actually have more energy out than you have put in. So you actually have the opportunity to do anti-Stokes measurements. Anti-Stokes lines. So the excited states are maybe even really in reach in terms of photon numbers. But you can see there's a more clearer signal here. This is another figure of the same application. You can see here that you do have a gain. Like you basically negative energy transfer means you have energy out of the model. So the laser excitation somehow have relaxed, but you did gain some of that energy, and that's what you see here, very noisy, obviously. So you can actually look at very short intermediates, and you can characterize these spectra. And of course your whole different spectrum not as congested as it would be if you only had one spectral axis. And the final state line broadening is much less than typically than the X-ray transition that you're using to generate a resonant Raman scattering. So the resolution could be much higher than what you get from X-ray absorption. Yes. This is the iron K edge. Hasn't been done as far as I understand. But LC-2 can certainly do this. This is actually an oxide. More in the realm what has simulates. But this is also highly interesting. Of course, hard X-rays have certain people into high pressure cells, very different environmental conditions. But they are still more challenging to get high resolution compared to field. So this is just inorganic chemistry, steady state ESRF measurement. But this is more of an opportunity side. So that's two. You have so many photons in this, and of course, this is not a borderline measurement anymore. Now you go from 100 hertz or so, 100,000 hertz. 3 orders of magnitude, 4. So this is 1s excitation, 2p fills the core, and then you have this iron 2p, which is an LH in this respect. And this is valence excitation here. So this would literally be 2p core hole filled, and then you have a valence excitation. So this is the LH resonance, and this is the M. This is the K. I think nonlinear optics is one of the science files say that is very interesting. Okay.